streets, I'm a mobster. You got 50 whole bed, you'll be my sponsor. Them snakes on the plane, me and Kanye Conda.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
In this video we'll explore friction, and let's start by looking at what causes it. So a classical example of friction is when we are pulling a block on a surface with some force T. And as you know, there's some resistance to the friction in the opposite direction. Let's call that F mu, the friction force. It originates from the unevenness of the two mating surfaces. So on a microscopic level, even smooth surfaces are somewhat rough, and these nooks and valleys tend to cling and catch on each other, and hence restricting the sliding movement. So let's have a closer look what happens when we start pulling this block. In this figure we have the pulling force T on x-axis and the friction force F mu on the y-axis. So we start with the zero force and start increasing the pulling force. What we see with the red curve is that the friction force increases as well by the same amount, effectively restricting the movement of the box completely. So it stays put until we reach some threshold right here, and then suddenly the friction force jumps down a little bit and begins this slightly erratic movement. But it has an average, as you can see, and that is denoted in this figure by Fk. So this is called the friction force kinetic. So when the force is, or when the box is moving, there is some force Fk. And what is Fk? Well, let's call it F mu k. So friction force kinetic is modeled as some friction coefficient in the kinetic case times the normal force acting on the box. And the normal force is the one that supports the box on the surface, and it's usually equal to the gravity acting on the box. So this is pretty straightforward. And what about the other case when the box is not yet moving? As we can see, the friction force increases to this crucial point, and we call that the value of the friction force at that point F mu s for static. And in that case, the friction force is F mu s, and it has a different coefficient, the static friction coefficient, multiplied by, again, the normal force. You should note that these two equations are not in the vector form because the F is in different direction than n. So these are basically only for the magnitude. And one has to deduce the direction of the friction from each situation separately. Of course, it's always against the direction of the movement. A few notes about these friction coefficients themselves. So they are, in majority of the cases, they have values somewhere between 0 and 1. And a smaller value, of course, meaning less friction. These are experimentally determined by sliding blocks of material on top of each other, for example. Also, the mu static is always greater than the kinetic, as we can see from this figure. it takes more force to overcome the static friction so that the box starts sliding. But once we get it moving, the friction reduces by the amount, which is the difference between these two coefficients. And there's also a third one, so that is called rolling friction, that acts between a rolling object and a surface. For example, rubber tire and asphalt on the road. So, and that is noted by usually by mu r. Typical value for mu r in the case of in car tires about 0.02, like this. And let's say if aluminum sliding on the concrete, for example, we're talking about 0.5, 0.6, just to give you an idea. The nice thing about friction when it's being modeled in this way is that it doesn't depend on the velocity of the object, like in the case of air drag, for example. So applying friction in mechanics problems is usually pretty straightforward, as long as you remember that F equals mu n, and you pick the correct coefficient of friction.
Please. Yeah. Overseas, nigga. Top floor, clear windows, nigga. Glass house.